Let us discuss in this video the approximation of irrational numbers. So why is this important? So we said that irrational numbers are numbers that have a non-terminating non-recurring decimal expansion. Okay, so here comes the problem. We just can't keep saying decimal numbers one after another. We just can't, even if we spent our whole lives saying digit after digit, we would never be done. That's problem number one. Problem number two is the devices we use to do computations, calculators, computers, and so on. They have a limited capacity to store numbers, okay? So even if we wanted to use a billion decimal positions, it's not possible because the computers will not accept it, okay? So then every calculation we do, we always use rational numbers actually, in reality, because they are always truncated, okay? Now, when we do theory in math, we use real numbers, okay? But in practice, we don't. So how do we approximate a given irrational number? For example, I mean, if it's given as a decimal expansion, you just truncate it wherever you want. But let's say I give you a square root of 2. And I want to approximate with rational numbers with 2 digits of precision. Okay, so this one we know already because someone did this before us. We know that the square root of 2 is approximately 1.41, 42, 13, and so on, okay? So what we are aiming for is the first 2 digits. So we want an approximation for 1.41. So let's see how we do this. Now, in the previous video, we said this property that in between 0 and 1, there were infinitely many rational numbers. And we proved this, saying that we could always find a number in between those. Okay, so we are going to use the same idea. So the first thing, let's do a rough estimate here. I claim that the square root of 2 is in between 1 and 2. I already told you, but let's assume I didn't know. This is my claim, okay? Why is this true? Because I just squared. And if I square the 2 inequalities, both inequalities, what I get is 1 less than 2 less than 4. And this is true, right? So then the square root of 2 lies in between 1 and 2. And now that I know that, okay, what I'm going to do, so the square root of 2 is going to be somewhere here. Okay, what I'm going to do is to pick a number that is in between. Okay, I'm going to do, this is 1 over 1. Remember what we said in the previous video? We said that if I compute 1 plus 2 divided by 1 plus 1, if I add together the numerators and then add together the denominators, I always get a fraction that is in between. Okay, so excuse me, this is 3 divided by 2, that's 1.5. 1.5, you see this one is terminating, no problem. I know right away that 1 is less than the square root of 2 less than 3 halves. Okay, so we have an approximation right there, but it's not good enough yet. What we are going to do now, we are going to zoom in here on this piece over here. And what we are going to get is the segment 1 to 3 halves, okay? And we are going to, so the square root of 2 is somewhere here. What we are going to do is to repeat the procedure and find the number in between that is going to be 3 plus 1, sorry, I wrote, it's 3 halves. 3 plus 1 divided by 2 plus 1, so this is 4/3. Okay, so 4/3, you can use a calculator, but you can also try to do it by yourself and say, well, is it bigger or smaller than, so 4/3 less than the square root of 2 if and only if 4 is less than 3 square root of 2. If we square both sides, that's 16 less than 9 times 2, which is 18. So we're good. It is indeed smaller. So what we are going to do now, we have a better approximation already. We are going to work on the interval 4/3, 3 halves. Let's use a different color now. Let's see. We zoom in. The square root of 2 is somewhere here. Okay. So we do the trick again. We add together 4 and 3, we get 7. And 3 plus 2, we get 5, 7/5. Okay. So this is 1.4. So it's a smaller. Okay. But we could do the same as before. We could do 7/5. Is it less than the square root of 2? Is you do. Okay, you do the details. So we zoom in again. Okay, and what we have here is 7/5, 3 halves. Okay, again, square root of 2 stays close to 3 halves. Wait. So if I compute the number in between these two, it's going to be 10 divided by 7. Okay. So when I do 10 divided by 7, this one turns out this one is bigger than the square root of 2. Okay, so square root of 2 is somewhere here. Okay. This you prove. Okay, we have already seen how to do that, so now you practice. And we can just keep going. Now we have 7/5, 10/7. Okay, the number in between is going to be 17 divided by 12. Okay, and so on. Now it's just a question. So this was the interval. And so on. So then now you decide, like, where is the square root of 2, which is going to be here. Square root of 2 less than 17/2. You do. And we can keep going for as long as we want. I did this for a few more rounds. What I got was 41 divided by 29 less than the square root of 2 less than 17 divided by 12. Okay, and the first number here is for the decimals are 1.41, 37, and so on. And the one on the right is 1.41, and then 6 is 6, 6, 6, and so on. That one is periodic. So that's about it. You see, we already got our approximation with 2 digits of precision. Okay, and what we are saying here is when you look, so if you look at the real line, and you look at the square root of 2, and you do a zoom in like very carefully, then you have the two numbers we found that are 41 divided by 29, and then we have the other number that is 17 divided by 12. And this, if we look this close, this looks like a rough estimate, but if we look from far away, for some purposes, it will be basically indistinguishable, okay? We can keep going, we can get as many digits as we want. But for that, it's better to do it on a computer. Code a small program that does it for you, because otherwise it gets tiresome. But I thought it was interesting to know how this was done before computers existed. Like, how can you do this on your own by hand? Okay, so if you put a couple hours, you will get so many digits.